Hey, in this video we are going to discover a complete webGL/webGPU solution that makes the process of the creation of 3D interactive web applications so easy and fun. Before we jump into the coding side of things, I suggest that you check this video out to understand what is WebGL and WebGPU in the first place and why we need a library such as Babylon.js in order to create 3D experiences on the web. And without any further ado, let's get started. First and foremost, we'll need to set up our project files in the server. To do that, I'm going to create a folder, then open the terminal and type npm vite create at latest. Next, we need to set a name for the actual project folder. Now, since I'm going to go the vanilla JavaScript way for this in my future tutorials, I'll choose vanilla here and then JavaScript. That done, I'm going to open the folder I've just created, start a new command line window and type npm install to install vite. And now I'm going to run npm run dev to start the server. The next step I'm about to do is install Babylon.js, so I'll stop the server by hitting Ctrl+C and type this command npm install -d at babylon.js/core. Meanwhile, I'll get rid of the files we don't need and empty the others. Now that the installation is finished, I'll run the server again. And there we go, we are ready for some Babylon.js action. To display a piece of 3D art on a web page using Babylon.js, we need 4 essential elements. The first one is a canvas element. It's an HTML container in which you show your masterpiece on a page. The second element is the engine. This is basically the brain of your Babylon.js app, which transforms the logic you type into living pieces of 3D graphics. The third element is the scene. A scene is the 3D space where the engine renders the 3D objects. And the fourth one is the camera. The role of a camera is to display a certain space within a scene. Having said that, let's put what we've just learned into action. So the first thing I'm going to do is create the canvas element. Now, in the main.js file, I'm going to import Babylon.js and assign the canvas to a variable. Next, I'm going to create an instance of the Babylon engine class and pass the canvas to the constructor method, so this way we are telling the engine to render the scene in this canvas element. Now I'm going to create this function in which we will do 99% of the work. So here I need to have a scene instance that has to be returned by this function. Next, I'm going to assign the returned scene to a variable, which I'll need in this runRenderLoop callback function. I'll explain why we need this method later in this video. That said, in here I'm going to call render and let's see what we've got so far. And there we go, the engine has rendered the scene into the canvas. However, we have an error message that says we still need to add the fourth essential element, which is the camera. But before we do that, let's actually make the scene take all the space available on the page. To do that, I'm simply going to use a few lines of basic CSS. Before we start introducing stuff to our scene, we need to fix something first. Let me add a camera and a box real quick just to show you what is the problem and how to fix it, but don't worry, I'll come back to that in a minute. So as you can see, we got this big box in the scene, but the problem here is that once I start resizing the window, the shape of this box in the entire scene actually gets distorted. So what I'm going to do to keep the same look of the scene's objects is simply call the engine resize method, and now our box maintains its original shape despite the change that occurs on the window's size. An object that figures inside a scene is often referred to as a mesh. It could be a box, a sphere, a complex shape like a torus knot, or even more complex like a model created using 3D modeling software like Blender. The good thing is that Babylon.js provides a big set of built-in meshes that we can introduce to our scene, so let's see how we can do that. To add a mesh, we just need to assign an instance of its class to a variable, and that's basically it. And as you can see, this is the list of all the built-in meshes that we can use. Now we can do some changes on the mesh by introducing a couple arguments to the constructor. The first argument here is a name, which helps to identify the mesh. The second is an object, and the third one is the scene. Now in this object we can alter some of the properties of our sphere, like the number of segments. Reducing the value of that property resulted in a loss of quality of the sphere, and that's because meshes are actually composed of a set of triangles made out of segments and points, aka vertices. The more lines we have, the more triangles we get, hence we have more details that define the surface of the mesh. Having said that, if I increase the number of segments, you can see that the sphere now looks smooth. Another property we can change is the diameter of the sphere. And we can also change the diameter based on a certain axis. Now back to the box. So here again we can set a name and an object with a set of properties, and by the way we can skip the scene here because when you have one only scene, the presence or absence of the third argument doesn't change anything. So in this options object we can set the size of the box. We can also change each component of the size individually using the width, height and depth properties. We can change the color of the box faces, so face colors here is an array of 6 elements. Every element is the color representation of one of the cube's faces. A color is made by using an instance of the color 3 or color 4 classes. The difference here resides in the opacity, which can be set by the fourth argument of the color 4 instance. The first 3 arguments represent the red, green, and blue channels of the color. Another way of making a color is to simply use the name of the color. Done with the box, we can add a ground which is defined by a width and a height. And we also have the number of subdivisions, which is pretty much the same as the segments property of the sphere. However, as you can see here, we can't notice the effect of this property, even though it is there. So to see how this property affects the ground, let me just add a couple lines, and I'll get back to them later on. This is our ground represented only by its subdivisions. Now let's reduce the number and see what we are going to get. That done, we can change the number of subdivisions horizontally and vertically. Now you might be wondering, why would we need such property if it doesn't affect the look of the ground? Well, it actually does once you want to change the positions of the vertices that compose the ground, like creating a landscape out of a ground where we have high and low areas. Speaking of landscape, we can do that right now using a variant of ground. It's called ground from height map. Yeah, another ambiguous term, I know. A height map is an image we sort of attach to a ground in order to set the height of each point composing that ground. It is made from a range of gray colors. Each level of gray represents the height of a point. The closer the color is to white, the higher is the point, and the closer it is to black, the lower it gets. So here I'm going to set an empty string as a name. The second argument is the path to the height map. In this example, I'm going to use this image that I already downloaded and put in the Babylon.js folder. As you can see, the ground is here, but it's not different from the first one, except a couple of vertices that are set at different heights, and that's because by default the number of subdivisions of the ground is set to 1. So let's change this to 50 and see the result. Now again, let's see the ground in the wireframe mode. As you see, a lot of details are shown by increasing the number of subdivisions, hence the number of vertices. Be careful though, because increasing the number of subdivisions requires more resources from the machine running the app. Another couple of properties we can set is max height and min height that affect the altitude of the vertices. We can make meshes out of text in Babylon.js. To do that, we need to have the font as a JSON file. So, say for example we want to use Montserrat, we'd need to download it from Google Fonts and extract the zip file, which I have already done. As you can see, I got a set of TTF files, so what I'm going to do is use this font file converter to generate a JSON file instead, and then save it in this folder. Now I'm going to load the JSON file, and since I'm using await inside this function, I have to add the async keyword in the function definition and also add the await keyword at the call. Time to create the mesh. The empty string is the name of the mesh. The second string here is the text render. The third argument is the loaded font, and the fourth is a configuration object. That didn't work because we have to add the Earcut module, so let's do that. Now, in this object, we can change the thickness of the text using the depth property. We can also increase the resolution for a smoother looking text. There are a variety of camera types in Babylon.js, but as a beginner you're probably going to stick to just 2 types. We have the universal camera, which is used in first-person shooter games. You choose the direction with the mouse and then use the arrows to move. And we have the arc rotate camera, which is defined by a couple of rotation angles, a target and a radius. So let me first remove the default camera and just leave a default light. To introduce a universal camera to the scene, we need to create an instance of the universal camera class, which constructor takes 3 arguments. The first one is the name, the second one is the initial position of the camera, and the third is the scene. Next, we need to allow user input by calling the attach control method, and that's it. As you see here, I'm moving forward and backward using the arrow keys. We can do the same with the mouse wheel, but we need to add this line first. We can also add an initial target for the camera using the setTarget method. Vector30 here is the same as vector3 with 0 at every component. Now, to create an ArcRotate camera, we need to make an instance of the ArcRotate camera class. The constructor here takes 6 parameters: the name, alpha, beta, radius, target, and the scene. I actually don't think the illustration I've shown you earlier is enough to make you understand how this type of camera works, so here's something better. So as you can see here, we have a scene with an ArcRotate camera set with these values, alpha and beta set to 0 and a radius of 20. The result of this configuration makes the camera 20 units away from the center of the scene, which is set as a target, so we understand from that that the radius is basically the distance of the camera from its target. Now, if I set the alpha and beta to 0, we get the camera positioned at the top and directed towards the origin of the scene, which is again the target. If we represent that using the 3D axis, the camera is going to be located at 0, 0, 20. Now let's change the value of the alpha and see how it will affect the camera. The camera rotates 2 pi or 360 degrees around the y-axis. That means alpha is the rotation of the camera around the y-axis that originates from the target that it's orbiting. Changing the value of beta rotates the camera pi or 180 degrees around the z-axis here, and that means beta is the rotation of the camera around the z-axis that originates from the target that it's orbiting. Now back to our code, we can actually use the setPosition method to position the camera using units, which is way easier than having to deal with rotations. We can set limits to the camera rotations, so setting the lower and upper beta limits will reduce the amount of the longitudinal rotation. Lower and upper radius limits, on the other hand, sets a minimum and a maximum distance between the camera and its target. A mesh is composed of two things: a set of points and lines that represent its shape, and a material, which is the layer that covers those lines and points. So for example, if we want to change the color of a mesh, we need to pass the color data to its material. So let me get rid of the text and uncomment the sphere's code. I'm also going back to the default camera and light. Now, to create a material, I'm going to create an instance of the standard material class, then assign it to the sphere. And as you can see, nothing has changed. However, now we are able to apply a lot of changes to our sphere. Actually, let's start by changing its color. And there we go. To change the color of the highlight spot made by the light, I'm going to use the specular color property. You have to keep in mind that these two properties are dependent on the light source of the scene. That said, let's get rid of the light and see what will happen. So we got a dark object as expected from an object placed in a lightless room. That done, let's bring back the default light, and now I'm going to add another color property, which is ambient color. Nothing new to notice here, and that's because we need to add an ambient color to the scene first, so let's do that. An important remark here is that the channel of the material's ambient color won't be effective unless the same channel of the scene ambient color is set to a value other than 0. So here only the green and blue channels are making a difference. We have also emissive color which colorizes the mesh even without light, and by the way, the value of this property is mixed in with the final result when you have another color set by the ambient color property, for example. So again, as stated in the docs, this is the color of the material as if self-lit, so if we get rid of the light source, we'll still be able to see the mesh. Next, we have the alpha, which is the opacity of the material. And we have the wireframe mode, which shows the skeleton of the mesh, I mean the lines and vertices that form its geometric shape. We can set a texture to a material using the diffuse texture property. To display a diffuse texture though, a light source must be present in the scene. Having said that, in case you still want your texture to appear without the need of a light source, you can use an emissive texture. To apply a texture to a box, we should do the same we just did with the sphere. However, if we want to apply a unique texture to each face, we have to use the face UV property. Face UV is an array of 6 vector 4 instances. Each represents a part of the texture that we want to assign to a face of the cube. So first, let's apply the texture to our box. As you see, this is our texture, which is an 800 by 300 pixels image. That said, what I want to do is divide this texture to 6 blocks, then apply each one to a face of the box. To do that, we need to store the coordinates of the lower left and top right corners of each block to a vector 4 instance, then push it to the face UV array. Now let's start with the first face. We got the first image mapped, but it's rotated. To reverse rotate it, I'm going to set the wrap property to true. And there we go. And now let's finish the rest of the faces. Sometimes you may want to move the texture to a certain direction, which is often referred to as texture offset. To show you how, let's set a texture to the ground mesh. So, to move the texture to the right or left, we need to apply a U offset. To move the texture up or down, we need to apply a V offset. We can also scale the texture using U scale to apply a vertical scale. Now, since I have already set a U scale, applying a V scale creates sort of a pattern out of the texture to cover the surface of the ground. And as I set U scale and V scale to 5, we got a pattern of 5 repetitions of the texture. It's about time to do some geometric transformations. So to translate the box, we need to set a value to the axis we want to move the object along. If, however, we want to apply 3 translations at the same time, we can pass a vector3 instance to the position property. The same thing needs to be done to apply a rotation. And also the same thing when it comes to scaling objects. A set of gizmos can be handy sometimes for debugging or maybe even shipped in the production version. That said, to add a position gizmo, we need to create an instance of the position gizmo class. As a beginner, that's enough to create the gizmo. However, it is recommended to pass a utility layer renderer to the constructor. I won't actually explain this in this video, but I may in future videos, so make sure to keep an eye on the channel. Next, we need to attach it to the mesh we want to move, which is the box in this case. And now we can move the box along the different axes. We also have the rotation gizmo and of course the scale one. As you've seen with the rotation gizmo, we have 3 axes to rotate around, but we can actually set only one, and that's by using the plain rotation gizmo. The first argument is the axis to rotate around, the second one is the color, and the last one is the utility layer renderer. Back to the render and run render loop methods. Same as videos, 3D scenes are actually nothing but a set of images, often referred to as frames, displayed at a certain frequency. Having said that, using this block of code, we are basically telling the engine to render 60 frames per second. Knowing that, we can use this information to animate objects in our scene. To do that, we are going to use the register before render method. The logic within the callback function of this method is run before rendering every single frame. So if, for example, we want to rotate the box, we'll need to increase or decrease its rotation value in here. This translates to rotate the box 0.01 radian 60 times per second. And that's one way of animating meshes in Babylon.js. Another way to do that is to call the create and start animation method, which arguments are the following: the name of the animation, the mesh to animate, the property to update over time, the number of frames per second, the total number of frames, the initial value of the scale or whatever property we want to animate, and the final value. So this means we are scaling the box from 0 to 2 along the x-axis. We have 120 frames to render the entire animation, and we are doing that by rendering 30 frames per second. Hence, the entire animation happens in 120 divided by 30, which is equal to 4 seconds. Another argument we can add is the looping mode. By default, it's cycle, which makes it loop infinitely. To make it occur only once, we need to set it to constant. And we can use an easing function, same as we do with animations in CSS. Another way of animating in Babylon.js, which gives more control over the animation, is the following. The first step is to create an animation instance, and here we have the animation name, the property to animate, the number of frames per second, the type of the property's value, and the loop mode. The next step is to create an array. Each element of this array is an object that has a frame number in the value. Actually, this is similar to a video player where the array is the seek bar and each element represents a point in that bar. The third step is assign the keys array to the animation. The fourth step is assign the animation to the box. And the final step is start the animation by calling the begin animation method. The arguments are the target to animate, the initial frame, the total number of frames, and a boolean that tells if it's looping or not. And that's it. Now if we want to slow down the animation, we simply need to increase the number of frames. Another important component that makes a huge difference when set right into a scene is the light. In Babylon.js, we have a set of different lights that we can use. We have point light, which emits its light from the source towards all directions. An example of that is a light candle. To create a point light, we have to make an instance of the point light class. The constructor takes 3 arguments, which are the name, the position of the source, and the scene. Babylon.js provides a gizmo for the lights to help visualize their positions and directions. So I'm going to create a light gizmo instance and attach it to the light. And there we go, we got the gizmo, and notice how that icon shows the directions of the light. The second light we have is spotlight, which is defined by a cone of light oriented towards a given direction. An example of that is a stage light. To introduce a spotlight to the scene, we need to create an instance of spotlight. The constructor takes 6 arguments: the name, position, direction, the angle of the cone, the decay of the light with distance, and the scene. We can also update the range, which is the maximum distance that can be reached by the light starting from its source. The third light is directional light. The light in this case goes from everywhere towards a given direction. An example of that is sunlight. To add directional light into the scene, we need to create an instance of the directional light class. Again, here we need to pass a name, the direction, and the scene. We have the ability to change the light intensity. Next, we have hemispherical light, which is the ambient light, and it's defined by a direction toward the sky. The second argument here is the direction. A couple properties we can use only with this light are the ground color, which is the color of the light in the opposite direction to the one specified in the creation. We have also diffuse, which gives the basic color to the scene objects. And we have also specular, which affects the highlight spot color. We can't talk about light without shadows, so let me first bring back the directional light and the sphere. For each light that casts a shadow, we need to create a shadow generator. So what I'm going to do here is create an instance of shadow generator. This argument basically defines the quality of the shadows. Low values make the shadows look pixelated. The second argument is obviously the light. Next, we need to specify which objects are able to cast a shadow by the light associated to the shadow generator. And we also need to specify if a mesh is able to receive shadows. Now we have a couple of properties to change the appearance of the shadows. An example of that is the darkness. It's the opacity of the shadows, in other words. Now if we take a look at the shadow, you'll notice we still have hard edges around it. To fix that, we can use a filter. And as you can see, now we have a smooth looking shadow, yet we still can do more to make it more realistic. Having said that, shadows in real life actually have blurry edges. To apply that to our shadows, we'll need to activate Use Kernel Blur, and then pass a value to the blur kernel property. Introducing fog to a scene can be a huge plus. That said, in Babylon.js there are 4 modes of fog. The first is none, which obviously means no fog. The second is linear. To add fog to our scene in this mode, we need to set a value to the fog start in fog end properties. Fog start defines at what distance the fog starts to appear. Fog end, on the other hand, defines the distance at which the fog totally hides an object. Next, we have exponential and exponential 2, which are pretty much the same. In addition to the modes, we have control over the density of the fog. And we can also change the color of the fog. Selecting objects using the cursor is so easy in Babylon.js. First, we need a pointer event, which could be a mouse move or click, or maybe a screen touch. That said, let's say we want to change the color of the sphere when we click on it. To do that, we obviously need to choose the onPointerDown event, then we'll assign a function to it. In this function, we are going to assign whatever object we clicked on at that exact mouse position to the hit variable. So hit here could be the ground, the scene, the sphere, etc. So we need to check what object is clicked on using the name as a criterion, for example. Now this may generate an error because the chosen object could have no name, like the scene for example. Thus we have to make sure it's a mesh first, and if it is, we'll check its name. The rest doesn't need any explanation at this point. Now, time to add some models. There are different file extensions that Babylon.js is capable of loading. The default one is .babylon, and we don't need to add a plugin to load models from this type of files, but it's not the case when it comes to the rest of the file extensions like .obj and .glb. So since I want to load a GLTF file, which is the most common file types to work with on the web, I'll have to install the additional set of loaders. To do that, I'm going to stop the server for a second, then type npm install -d at babylon.js/loaders. That done, now I need to import the module I've just installed. Next, I'm going to call the import mesh method and pass 4 arguments. The first argument here is the specific mesh to load from the model, so since we want to display the entire model, we have to set this to an empty string or null. The second one is the root URL. The third argument is the file name. And the fourth is the scene. Now, say we want to do some stuff by the end of the loading process of the model. To do that, we need to pass a callback function that takes 4 arguments. So, as you can see here, we have the model stored as the first element of the meshes array. And here we can scale it down, for instance. And we can also play another animation. Another variant of the import mesh method is import mesh async. Keep in mind though that both of these methods are asynchronous. And again, to play another animation, I'm going to assign the animation groups to a variable and then play the fourth one this time. Time to play some ambient music in the background. To do so, I'm going to create an instance of sound and pass the following arguments: the name, the location of the file, the scene, a callback function for when the loading process of the file is finished, and an options object. And here we can set the song in loop if it starts automatically once loaded, and the volume. In a lot of cases, you'd want to change values in real time to get the result you want to achieve. An example of that is the tool that I've used earlier to explain to you the elements of the arc rotate camera. That UI is called the inspector, and it's one of the best features in Babylon.js. To add that UI to our local app, we need to install the inspector module. So in the command line, I'm going to type npm install-d @babylon/inspector. That done, we need to import the module, of course. Then I'll just add this line of code right at the end of the code base. And now we can access every component of our scene with this well-organized UI. So here I'm going to mute the background music. We have the list of the animations available with the model. We also have access to the textures, materials, lights, cameras, etc. Furthermore, we can take screenshots, record videos and GIFs, and export the entire scene as Babylon, GLB or GLTF file. The beauty of Babylon.js doesn't only lie within the core of the library, but also with the toolset it provides. For example, we have the playground, which is super useful for collaboration. This is the basic template, so let's update the code by commenting out these lines, for example. Now, say I want to get some help from the community regarding this example. I'll just save this project, then get the URL and share it with the world. Pretty easy and very handy. Another gem that belongs to this toolset is the Sandbox, which is useful to inspect the models you want to use in your projects. And with this, we reach the end of this first Babylon.js tutorial on this channel. So make sure to like, share and subscribe, and I will see you in the next video.